So this video is on average atomic mass. Key concept, when you look on the periodic table, this is the atomic mass given for beryllium, this is for hydrogen. There are no atoms of hydrogen with that mass, there are no atoms of beryllium with that mass. However, that is their average. Just like if you were to get an average in my class this year of 97.732 according to my calculator, that doesn't mean you got a 97 on anything. That's important, because we're going to be using these numbers, and you have to understand that whenever we use them in calculations, we're assuming we have a rather large sample, and this average is an accurate mass for the average beryllium atom in our sample or hydrogen atom in our sample. A little bit of background here. Isotopes. What are isotopes? They're atoms of a particular element. They have the same number of protons, but the number of neutrons is not the same. So, when you look at this symbols, this isotopic notation, the bottom number is always your atomic number. The top number is always your mass number. The atomic number is the same as the nuclear charge. That's really important. The nuclear charge is the atomic number, but also is equal to the number of protons. So each one of these isotopes has one proton, because the atomic number, which we're going to call Z this year, you'll hear that a lot, okay, has one proton. Now the mass number is equal to the neutrons plus the protons. So if something has a mass number of 1, like this isotope called protium of hydrogen, and has one proton, well, we can infer that N must be equal to 0, because 0 plus 1 equals 1. Or we could just subtract this number from this number from this number. Anyway, this has 0 neutrons. For this one, we can assume that there's 1 neutron. We could subtract the 1 from the 2, or we could simply say, well, if the mass number is 2 and there's 1 proton, there must be 1 neutron. Whatever way you want to do it. And this one has 2 neutrons. One thing you want to note, since the average for hydrogen is 1.00792, we can pretty much assume that this is the most abundant of the isotopes. That doesn't mean the other ones don't count in the average, otherwise the average mass would be 1 spot on. Even that wouldn't be true, but I'm not going to get into that right now. All right, how do we understand or know what the average atomic masses are? How do we determine those? Well, you're going to get the data primarily, but you should understand a little bit about how that data was obtained. And what you need to do to get an average is you need to know the masses of the individual isotopes and their relative abundance. And the way you can do that is by using a mass spectrometer. The mass spectrometer will tell you the relative mass and the relative abundance. Watch how this works. You put a sample of an element here. By the way, it doesn't have to be an element. This is used in all sorts of other fields like forensics and conservation, art, chemical analysis, etc., etc. But for our purposes, if we get the basics, maybe if you decide to become a chemist later on or a forensic scientist, you'll use one and know a lot more than I do. But the fundamentals are always the same. A sample enters, and the sample is both heated and slammed with an electron beam. And what that does is it ionizes the sample. Essentially, it turns it into a bunch of cations. Cations are positively charged ions, and because of that, now that they have a charge on them, because it literally just rips the electrons off the atoms. So once the electrons are ripped off, all you got left are the neutrons and the protons, so the charge on the particle is going to be positive. Now, once there, we're going to accelerate. And the reason why we can accelerate is because we have 2 little disks here, and one of them is positive and one is negative. And what essentially will happen is, as the sample is pushed through into here, the positive plate will repel the sample while the negative one attracts it. So essentially we're going to be pushing it forward while pulling it to the right as well, and that's going to make it move faster. Then what we do is we deflect. I don't want to confuse you. I almost did this before. Things that weigh less will be deflected more. So the magnetic field is going to deflect the lightest ions the most. So if you were to put, let's say, these 3 isotopes in your sample and put them through this thing, you would expect that this one right here would be the one that would end up over here, because it bent the most. So the bend was a bigger angle here. So you would know how much protium was in the sample. And the 4th step is to detect. Now the detection, based upon the bending and a lot of math, they can basically figure out by the bending what the mass of the particle actually was, and the detector will also be able to indicate how much of that particle was present. So we're going to detect both the mass by the degree of bending, all right, and the second thing that you can tell is how much of each thing there is. Okay, so that is the quantity, or what we'll probably here call the relative abundance. So the detector can detect how many particles hit it at a particular spot, and that can be recorded. It comes out as a digital print, or basically comes to your computer screen. Now, you should have a calculator here. A weighted average is always done the same way, whether you're doing students' weights, ironically, or you're doing a weighted average for the mass of an atom. It's done the same. Essentially, you're going to take this times this plus this times this plus this times this and put it over the total. You learn this in trig. It's part of the trig exam. It's not supposed to be difficult. So I'm going to pause this and let you do the math and figure out what the weighted average for these the 19 students in the class. Before you get your answer, though, you should recognize that because there's a lot more 140s than there are 120s, your weight should be somewhere in the 130s. And this way you'll know if you made a calculator error. So when I do this one, I get 132.6, and that's probably pounds. I'm assuming it's not ounces. All right. And that is the class average. Well, this is done the exact same way, except in this case, the number of students is basically the percent abundance. And these are the individual weights or masses of the individual types of isotopes of a particular element. And you should be able to identify the element. And the way you're going to do this is you're going to go this. I'm not going to write it all out, because you should put it in your calculator. It's going to be this times this, plus this times this, plus this times this, plus this times this. So it's basically mass times abundance plus mass times abundance. Now, your choice. I don't like working in percentages. So when you're done with dot, 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 there's 4 of these guys you're going to do, and you're going to put the whole thing over 100, or you can convert your abundances into decimals, in which case all the abundances will add up to 1 instead of adding up to 100. So you'll take the whole thing and then divide it by 1 and get your answer. I would suggest you pause and see if you can do it, and then we'll identify the element and get the answer. So when you're done with all this stuff, and I suggest you use a lot of parentheses here to make sure you get it right. Before you get started, though, you should know your average has to be somewhere between 3.9 and 207.9. It's got to be between those two numbers. So if you didn't get that, you made a mistake. The other thing you want to notice is 52% of the atoms weigh almost 208. Another 22% weigh about 207. So your average should be either high 206s, low 207s. And when I looked this up in the textbook, and that's what I did because I'm cheating here, the correct answer that you get is 207.2. That's units or AMUs, and that can be ascribed to PB or lead as your answer. Again, if you didn't get this, go back and try it. You know what the answer is, and that's something I want to emphasize here. Like, I gave you even-numbered problems. The good thing is you get the answers for the odds in the back of the textbook, and they sort of mirror each other. So if you can't do question 38, well, try to do number 37 and look up the answer and see if you can handle that. A couple of tricks that show up in some of these average atomic mass questions. They love the 2 isotope trick, because you think you have 2 variables. You think you have, okay, like let's say, what is the average atomic mass of, I think this is boron. It might be beryllium, but it really doesn't matter in this context. I'm not going to bother looking it up. All right. So let's say you, or actually you do, and you know there's 2 isotopes. So you have isotope 1 that weighs 10, isotope 2 that weighs 11, and you want to know their relative abundances. Well, you could call this X and you could call this Y, but then you have 2 variables. But since the 2 percentages, and you can obviously take this whole thing and divide it by 100, or you can keep it in decimals. I like decimals, so I'm going to do it that way. You'd be like, oh, 10 times x plus 11 times 1 minus x, because you only have two isotopes, and that will be equal to 10.81, and you can distribute and solve the problem. Okay, what you've basically done is a algebra 1 let statement. Let the abundance of isotope 10 be x, and let the abundance of isotope 2 be 1 minus x, and then plug it in and solve. Make sure you're clear. The percentages will always add to 100. So if you have I know there's one question with a column, be aware that column of percentages must add up to a total of 100. That should be enough to get you through average atomic mass. The next video will be the mole.